Now that we have a little experience with our graphs and graph of a quadratic and even graph of an absolute value, we should be able to now move those graphs around and start looking at their equations a little more. So that's what we're going to be doing, and finding some patterns, finding some new equations we can use in this section. So in 6.3, we want to be able to use the graph translation theorem to interpret equations and their graphs. And not only just the parabolas, but that's what we're going to stick with mostly because those are our general quadratics. Yes, we did the square root graphs. Yes, we've done the absolute values. We'll just touch on those a little and show how they compare as well. So let's get started with, we know the most general equation for a quadratic is y equals ax squared. Basically, again, the bx and the c are zeros. So we know y equals ax squared plus bx plus c is our standard form of an equation. But if you put a 0 in for b and c into this equation, the resulting equation gives us just y equals ax squared. So a parabola could open up, could open down, but here we go. Right now we are assuming that we have a positive. Now when I say that, it's because this now is our equation. Let's assume y equals x squared. If y equals x squared, then we have a y value that allows it, or an a value that allows it to open up. 1 is positive. It goes through 0, 0. We have our points, 1, 1, 2, 4. You can see it's just slightly off, it looks like, on the graph. 3 would be 9. Negative 1 would be 1. Negative 2 would be 4. Negative 3 would be 9. So there's our equation, and it's graphed. Now the question is, if that's just the general one, what happens when I now make it y minus a quantity, y equals the quantity of x minus 3, that quantity squared. So instead of just x squared, I have something else in there. So go ahead, if you have your calculator out, x minus 3. Go ahead and see what happens, because this is part of a discovery. And you should be able to tell me that it looks like it's the exact same one, because we still have our x squared that we had up here. But when we take this graph, it is now, you should be able to tell me, 3 units to the right of where it sat before. 3 units right. So that graph was the exact same shape, exact same width, opens up, but is now positioned 3 to the right of where it used to be. Okay? All right, let's just bring that down here for now. Again, now what happens? Y equals x squared plus 3. What if that's our original equation? So it matches our y equals x squared from up here. Okay. But it also has that plus 3. So go ahead and graph that with the help of your grapher. Or if you have ordered pairs, do it with your ordered pairs. And this time, you should be seeing the result that your equation has moved up 3 units on your y-axis from where it was before. It is still the same width. It's still opening up because of the x squared. The a value is still a 1. Nothing's changed there. But now what we could say is, instead of that 3 being in the parenthesis as it was on this line, on this equation, it is now outside of the parentheses, sort of by itself, attached to the squared statement, and it went up. So these are characteristics you need to look at. All right, let's move that one out of the way. And let's reveal our last but not least. Now this time, what's going to happen when we put both pieces together? We take and add something in the squared component, and on the outside of the squared component. So if you notice what we did last time, you should be able to make a good hypothesis about what's going to happen. So if we just do that math, well, it went 1, 2, 3 to the right the first time, and now it went 1, 2, 3 up. We're looking at a new parabola that is equal distance. A value is still the same. It's still opening up. The width between the two branches is the same, but it is now 3 to the right and 3 up from where it was originally. Now, in case you haven't heard this, we like to call the original graph the parent graph. Okay, so that basic equation, when we said y equals x squared, and that was our original graph here, we knew all the characteristics of that. So now when we start graphing any of these other ones, we now will base that on that parent graph, original graph that we started with, because they all come from that in essence. So what you need to observe is that when you had your number in the parentheses, that moved it 3 units to the right. When the number was outside of the squared term and it was a positive 3, it moved it 3 units up. Now, some people will also like this form of the equation. It looks a lot like vertex form of a line. So notice, the only thing I did was move this 3 from the right-hand side over to the left by subtracting 3, and I now get this new equation. This new equation looks a lot like vertex form. Y minus y equals a times x minus x, the quantity squared now, versus before we didn't have a square because it was linear. Point slope form. So it mirrors that exactly, and it has those same characteristics. So if I see it, everything on the right-hand side, this would be a plus 3. If I moved it over here, it's still, you're going to say, is a plus 3. Yeah, because remember, y minus hk is how we memorize this. So that would be our slope, and x minus h, the quantity squared. So there's point slope form. It looks exactly like it. So those h and k values, wherever you place them, are going to indicate how you move. This, whether it's inside or outside of the squared, is going to dictate how you move away from that origin, that 0, 0 point. All right, knowing that, let's try and regroup. From that activity then, y equals ax squared was graphed as a parabola through the point 0, 0. It opened up or down based on the a value. R's opened up. When x was replaced with x minus h and y by y minus k, the equation became y minus k equals a times the quantity x minus h, that quantity squared. This equation is nothing more than the original under a translation of hk. How far has it been slid? Left or right is h, and k is up or down. H is the left or right movement. K is the up or down movement. The two graphs are congruent since they are translated images. You're not making them bigger, smaller. And a translated image is always congruent to its pre-image or parent graph. This equation will now be called vertex form of a parabola. So if they say write in vertex form, it's because you can look at that and say, oh, I see where it went. It went to h, k, from where it was originally, which is always, you got to remember, 0, 0 in this original form. So the vertex in y equals ax squared is 0, 0. The vertex over here is always where your hk ends up. couple good things to remember moving us forward in graphing. All right, here is just a graph that sort of puts it all together. If we now have these two equations, y equals ax squared and y minus k equals a times x minus h, the vertex form. So this is the original or parent graph. And this is now vertex form, the one that's been translated. These are characteristics you should be able to show. The vertex originally was 0, 0. When we move it hk units, it becomes that hk. Very easy to see. If a was greater than 0 to begin with, the graph opens up and has a minimum point. Nothing changes over there because a is still a. If a is less than 0, it opens down, maximum point. Same on both. Line of symmetry, this one started out as the y-axis because if it's right at the origin, and there's the y-axis becomes our point of symmetry. As soon as you move it, hk, so as soon as you take a parabola and move it h units, let's say to the right, and k units up, we're over h and we're up k. And if that's our new point, then you got to remember that new line of symmetry is x equals h, that h value. X equals a number is always a vertical line, and it's however many spaces you moved it, h, and that would be your new line of symmetry. So that's where we get our vertical line. And last but not least, the a value determines the width of the parabola, how tight that parabola will really be in relationship to the y-axis. All good things to notice going forward. So you don't have to graph every single one. Now, using this graph translation theorem, we have the quadratics. Y equals x squared is a good parent graph, and this would be the translated version. The absolute value, we have y equals absolute value x, and this would be the translated version. And then the square root, y equals the square root of x, and then there's your look for what it would look like if we use the translated version. Notice they're all very similar. The only difference is what symbol's being used, the parentheses, the absolute value bar, or the square root. Okay? So a little more work definitely with graphs in this section. So if we were to go forward and say, look at this. This is an absolute value function. And says, how do you think the parent graph will change? So we'd like you to hypothesize, but before you hypothesize, you want to look for a pattern. So you start looking at the functions, f of x equals. They're all written that way. Then notice, they're all written with an absolute x, which is sort of like our parent function, and then they have something outside of it. So if we were to go through and graph these, and I ask people to come up, you could take, for example, the pink. Whoops, got to grab the pink. See if it'll come. And we will move it to where we believe it should be. And if it's outside the absolute value, +2, sorry. It's going to be going up there. And you can move each one accordingly based on you knew what the parent graph function was, and you can move them. There's a pattern to the equation, and you should be able to see without even going to your grapher. That's the key. How these will look. Same thing now if I switched it up. Now take a look. The function f of x equals. Then now I have an absolute value, and whatever is happening inside that absolute value. We like to say in and affecting x. So if you had your original parent graph drawn, which we do, you could then get it a little more accurate here to start with. You could then place your other, and again, pink one here, if we go x plus 1, and it's inside, that to me looks like we are going to have a shift to the left of 1 unit, and 1 unit to the left puts my absolute value right on the origin like it was, done. And you can continue to do that with all the others as you go. So without even needing a calculator to do those. So this one is absolute value of x. Notice on this one there's a slight change. We sort of try to mix it up a little. Now you have a negative. Remember what a negative on the a value does. Here you have a negative. Here you have the plus 4 on the outside of the x. So we'll be placing a few of those in class as well. But you should be able to identify without using your calculator where those end up quite easily. And that should leave more with the a values changing. So that is definitely talking about what is the width. That's what we learned with the a value dictates there. So if we put everything together, absolute value function makes the shape of a v. Good. And if it makes the shape of a v, the parent graph function for all absolute values is nothing more than f of x equals the absolute value of x. There's the general formula for vertex form. How do the following affect the parent graph? How does A affect the parent graph? A affects it two ways. If it's negative, it'll move it down or up if it's positive. The A value also makes it a wider V or a skinnier V. The H value slides it what? Left or right. And the K value moves it up or down. So in every single one of these, without using a calculator, you should be able to go through and say, oh, from the original parent graph, which we're starting with up here, we would know in choice A, this moves 1 to the right. Same shape, same everything. It's just moved, slid. Think of it that way. Doesn't get wider, doesn't get skinnier. All right? That's what you should be able to do, and that's what we'll be asking you on in class. All right? So this is sort of that same thing we can use again in class. All right, now here, this is just an example. We've talked about these different transformations, linear and absolute value now. Match the function with the correct real-world example. So if we go linear functions, which of these are linear? So you're looking at A, B, C, D, E, or F. And then which ones are absolute value functions? And we probably could say which ones are quadratic functions. So you should be able to handle all those, and we will be discussing those more in class. Another, here's some quadratics. Different than the lines, different than the V's. All right, real-world shapes that are quadratics. And you should be able to see those as well. So if I would just select any one of these, for example, the fan, you can see what happens there. The ski, the helmets. So you're looking at things that have quadratic shape that you may not have even thought about, but they are truly quadratics. And last but not least here, 4 of these pictures contain quadratic functions, but 2 do not. Can you spot the knots? So start looking. We need quadratic. Parabola-shaped graphs. Where do we see parabolas? So if you're saying, can we spot the knots? I hope you have chosen this slide and these windows. And the windows is because they're a little too straight up and down. Parabolas never become quite straight up and down. Okay? So we'll do a little with those pictures and resetting some of those graphs in class. Please come with any questions you might have in regards to that.